Welcome back to Practical PyTorch. In this video, you'll see why a plain, dense network is the wrong tool for images. We'll look at how an image is stored as numbers, what happens when you flatten it for a dense layer, and what the grid was quietly telling us all along. A photo is really just a grid of numbers. This one cell holds a single number. This cell sits right next to it. In the picture, these two touch. But if we flatten the grid into one long row, the layer is never told they were side by side. It would have to learn that from nothing. This video has 3 parts. First, how an image is a grid of numbers, its pixels, its color channels, and a batch of many images. Second, what happens when you flatten that image for a dense layer. The number of weights explodes. Third, what the grid was telling us, which pixels are neighbors, and how the same shape can appear anywhere. Let's start with the picture itself. Before any layer touches it, an image is just a grid of numbers. A real image is large, 32 rows by 32 columns or bigger. Each little square is 1 pixel. We shrank it to 8 by 8 here for one reason, so every cell is big enough for you to read. Look at one cell. It holds a single number, and that number is 1 pixel. The cell right beside it holds its own number. 1 pixel, 1 number, that's simple. Later we'll come back to how these touching cells work together. These numbers run from 0 to 255. That range is one common way to store an image. The rule is simple. 0 means black. This cell reads 0, so in a real photo that pixel would be black. And 255 means white. This bright patch is all 255, so it shows up white. Low numbers are dark, high numbers are light. Layers like decimal numbers, not whole numbers from 0 to 255. So we divide every pixel by 255. Now the D-type is float 32. The smallest value is 0.0, and the largest is 1.0. The picture did not change at all. Every number just moved to a new scale, from 0 to 1. A color pixel is not one number. It is 3. How much red, how much green, how much blue. So the single grid becomes a stack of grids. Behind the front grid sit 2 more grids, one for each of the other colors. 3 planes in all, one for red, one for green, one for blue. Each plane is still the same 8 by 8 drawing we used before. The 32 by 32 on the shape chip is the real image size. This new direction, running through the stack of planes, is called the channel axis. We write it as the letter C. So the shape reads CHW, channels then height then width, 3, 32, 32. When you train, you rarely pass one image. You pass many at once, a batch. That batch adds one more axis, and it goes in front of all the others. We call it n, the number of images. Now the shape has 4 numbers, n, 3, 32, 32. PyTorch always orders a batch of images the same way. N, C, H, W batch, then channels, then height, then width. Hold on to that order, the rest of the video leans on it. One color image has 3 axes. Its shape is 3, 32, 32, 3 planes of 32 by 32. A batch of 64 of those images has 4 axes. Its shape is 64, 3, 32, 32. So one image is 3 axes. A batch is 4. The batch just adds that count in front. So far the grid has cost us nothing. Now let's flatten it for a dense layer and watch the cost jump. A dense layer cannot take a grid. It only takes a flat row of numbers. So first we flatten the image. Flatten unrolls the whole grid into one long line, every pixel laid out in a single row. How long is that row? Count the pixels. The image is 32 wide, 32 tall, and 3 colors deep. 32 times 32 times 3, which is 3072 numbers. That is the width of the input row. A dense layer gives every input its own weight to every output. With 3072 inputs and 128 outputs, that is a huge table of weights. Multiply them out and you get 393,216 weights for a single layer. A convolution filter is tiny by comparison. It is 3 by 3 across the 3 colors. That is all it looks at. 3 times 3 times 3, which is 27 weights, and the same 27 are reused across the whole image. Put them side by side, 393,216 against 27. That is about 14,000 times fewer weights, and the smaller one still keeps track of which pixels are neighbors. It wins on size and it keeps the grid. You don't have to trust the drawing. Ask PyTorch. The dense layer's weight count comes back as 393,216. One convolution filter comes back as 27. Divide one by the other, and it is about 14,000 times. To be fair, a full convolution layer has many filters. Even 128 of them is only 3,456 weights. 3,584 counting its biases, still about 113 times fewer than the dense layer. The convolution is smaller, but size is only half the story. Let's see what else the grid was quietly giving us. These 9 cells all touch, right here in the middle. 1 pixel on its own tells you very little. But 9 that sit together can form a shape, an edge, a corner, a stroke. The meaning lives in the neighbors, not in a lone number. Now flatten that grid into the row again. The 9 neighbors that made a shape are scattered. 2 cells that were touching can end up far apart in this line. The dense layer sees only the row. It has no idea those numbers were ever neighbors. It has to learn that from scratch, from the data. Think of this bright patch as a little shape. Right now it sits in the middle of the picture. But the same shape could sit anywhere, like down here in the bottom right. It is the same shape wherever it lands. A convolution learns that shape once and uses the same filter in every position, so it finds the shape wherever it sits. One trap catches almost everyone. NumPy and PIL give you an image as height, width, channels, but a PyTorch convolution wants n, c, h, w. Feed it in the wrong order and you get a runtime error. It expected 3 channels but got 32 because it read the height as the channel count. Put the axes in the right order, n, c, h, w, and it runs. The output shape comes back as 1, 16, 30, 30. The real danger is worse. The wrong layout does not always crash. When the height happens to be a legal channel count, it runs anyway, quietly wrong. Let's pull it together. An image is CHW, channels, height, width. A batch adds n in front, giving n CHW. Flatten it into a dense layer, and the weights explode. 393,000, 216 against 27. And a dense layer forgets which pixels were neighbors. That is why it is the wrong tool for images. The next video is the fix. Your turn. A 32 by 32 color image is flattened and fed to a dense layer with 128 outputs. How many weights is that? And how many weights are in one 3 by 3 filter over the same 3 colors? Pause and work it out. Okay, here it is. The dense layer needs 393,216 weights. That is 3,072 inputs times 128, plus 128 biases. The filter needs just 27, plus 1 bias. About 14,000 times more, and the small one still knows which pixels were neighbors. So the fix is a small grid of weights dragged across the whole image. That is called a convolution, and it is the next video. It is small and it remembers the grid. I'll see you there.